This geometry video is about the topic of interior angles of a convex polygon. More specifically, we're going to look at the triangle sum theorem and then the polygon sum theorem. So here's a triangle. Notice that it's totally dynamic. I can adjust any of the three vertices, making it an obtuse triangle, can you do it? So close. Pretend I could do it. A 90-degree angle would be a right triangle, and then an acute triangle. So this could be used for any of those three cases of a triangle. And what I want us to look at here is I'm going to calculate the sum. And GSP is really nice because you can click on any of these dynamic measurements and add them to the calculation. And so I'm going to add these three together. And what do we get? Very important number. No matter how we change or manipulate this triangle, the three angles always add to 180, and this is called our triangle sum theorem. The three interior angles of a triangle always add to 180. Alright, that's one to remember. Now let's apply this to some other polygons. And these are irregular. This one's a quadrilateral. Over here we have a pentagon. And to help you see how we're going to use the triangle sum theorem, what I'm going to do is from one vertex, I'm going to draw all of the possible diagonals. And notice now what we have. Come on, marker. There we go. I have two triangles making up the interior of this quadrilateral, and I have three triangles making up the interior of this pentagon. Now, each triangle, if I were to add the interior angles, each one would give us 180 degrees of interior, so I can figure out that the sum of the interior angles of a quadrilateral is going to be 360, no matter what kind of quadrilateral it is. For this pentagon, we have three triangles, each one having interior angles of 180 degrees. And yeah, we'll get faster here in a minute. So 3 times 180 is 540. So what we're doing is we're applying this triangle sum theorem to other polygons in order to get the total interior degree measurements for all 5 of the interior angles. So let's get rid of this ink. And oh, help me remember. 2 triangles in a quadrilateral, 3 triangles in a pentagon. Okay, there's a little pattern here. Okay, now let's get rid of this ink. And let's go to some larger shapes. And let's use the same technique. So from any one vertex, just got to choose one. Let me use the mouse for this. I want to divide this interior with as many diagonals as possible. And then let's use this one. So we're dividing up this interior. Stop me if you know the answer already. And now how many triangles do we have in this hexagon? 1, 2, 3, 4. So remember, n is going to be our number of sides. And we have 6 sides making a hexagon. And how many triangles did it take to complete or to fill this whole interior? 2 less than the number of sides. And now let's count up the number of triangles here. 6. This originally, I guess it still is, an octagon. So number of sides, we're going to let that be letter n. And we have 8 sides, and the number of triangles is 2 less than the number of sides. So let's now look at our new theorem. So, and remember, we must have convex polygons, and we're letting n equal the number of sides or angles. S is going to be the sum of the interior angles. So what we have is 2 less than the number of sides times 180 degrees.